Alright, so today we're going to talk about infinite limits. Okay, so I'll give you the general description of it first, and then pretty much it's kind of self-explanatory, because normally our limits would go towards a certain number, either up towards a number but never pass it, or at some point just get really, really close but never touch it. Here, when you approach a certain number, it'll either shoot up to positive infinity as it gets closer, or either negative infinity. So pretty much the same approach. You just plug in values from the left and values from the right, and you'll see the number either shoot really high or shoot really low. That's when you know it's infinite. Okay, so let's say if we let f of x be a function that is defined at every real number in some open interval containing c, except right at c. So it's defined everywhere except at some value c. So in other words, the statement, the limit of f of x as x approaches c equals infinity, that just means for any, let's use m to just represent any big number. It could be a million, a billion, a trillion, just a really big number. So for any really big number greater than 0, so m equals a really large number, then there exists some f of x that's greater than that number. Okay, so if we were to graph that, so you have your x-axis and your y-axis, and let's say this is our c value. Okay, so we know if we plug in c, we have denominator equals 0, which you just can't have. Okay, so as you get closer and closer to c from the left, the value just gets higher and higher. And as you get closer and closer to c from the right, the value just gets higher and higher. So they're saying no matter how big you make a certain number, at some point, if you just keep getting closer and closer to whatever that c value is, it's going to pass it. So if you move that m value up a little higher, or even a lot higher, at some point, it's still going to pass it. So that's what they mean by it just equals infinity. No matter what, it's just going to keep growing. All right. Any questions on that one? All right. I'll leave that up for a second.
So what do you mean by it will pass it?
Oh, the number will just keep growing and growing. So if you set that for a billion, and if you have some function to where it'll never equal c, if you plug it in, it'll be undefined. Right. If you get closer and closer to it, at some point, if you plug in some point 0.0000001 or whatever it is, you'll eventually pass a billion. So if you move it up to a trillion, if you get even closer, it'll eventually pass a trillion. So no matter what, you'll get closer and closer, it'll eventually pass that M value, no matter how big it is. To be honest, it'll just eventually just keep going towards infinity.
Okay, so it will never like pass C from a direction, are you saying, or?
I don't know, C is just a value that it just can't equal.
Right.
It's one of those, if you plug it in, you'll get a denominator of 0.
Okay.
But remember, when you get a limit, you're getting really, really close to it. You'll never reach it, but you'll get really close. And normally, we've had limits to where if you get really close, it could equal 2 or it could equal 4. This way, when you get really, really close, it'll just keep getting bigger and bigger and bigger.
Okay.
Does that make sense?
Yeah.
Okay. I'll do an example and hopefully it'll make a little sense. All right. Oh, quick note. That when you see the limit of f of x as x approaches c equals infinity, it doesn't mean the limit exists. It actually means the limit doesn't exist. Or there is no limit. All right, so let's do a quick example. It's over here. Okay, so let's say, for example, you wanted to find the limit of 3 over x minus 2 as x approaches 2 from the left, and the limit of 3 over x minus 2 as x approaches 2 from the right. Okay, so we know we can't just plug it in because we'll get a denominator of 0. Okay, so we'll call that A and we'll call this one B. Okay, so for the limit 3 over x minus 2 as x approaches 2 from the left, let's create our little value table. Okay, so you have value of x and you have your f of x, which is just 3 over x minus 2. Okay, so as you're approaching it from the left, okay, so just a quick little number line here. If you're approaching it from the left, you're getting 1, 1.9, 1.99, 1.999. It's getting really, really close to 2 from the left. So let's say we start at 1.5, 1.9, 1.99, 1.999, and 1.99999. So we're really close to 2, just not equaling 2. Okay, so if you plug in 1.5, you'll end up with -6. If you plug in 1.9, you'll actually end up with -30. If you plugged in 1.99, you'll end up with -300. 1.999, you actually end up with -3,000. And 5 nines, you'll end up with -300,000. Okay, so if you just keep adding 0.99999, that number would just keep getting smaller and smaller and smaller, approaching negative infinity. Okay, so we know that the limit of 3 over x minus 2 as x approaches 2 from the left equals negative infinity. And that's because the value just keeps getting smaller and smaller. The closer you get to 2. All right. Any questions on that one? Okay, so let's say for question B, create a little bit of a barrier there. Say the limit of 3 over x minus 2 as x approaches 2 from the right. Okay, so if we have our x value up here and our 3 over x minus 2 here, but on this side we're going to approach it from the right. So we're going to have 2.1, 2.01, 2.001, 2.0001, so we're getting closer and closer to 2, but this time from the right. Okay, so let's say, sorry, 2.5, 2.1, 2.01, 2.001, and 2.00001. Okay, so if we plugged in 2.5, we'd actually end up with positive 6. If we plugged in 2.1, we'd end up with positive 30. Okay. If we plugged in 2.01, we'd end up with positive 300. If we plugged in 2.001, we'd end up with 3,000. If we plugged in 2.00001, we'd end up with 300,000, positive 300,000. If you plugged in 2.00001 and then added more zeros and put a 1, you get closer and closer. That number will get bigger and bigger and bigger. Okay, so we know that the limit of 3 over x minus 2 as x approaches 2 from the right is equal to positive infinity. Only because the value just keeps getting bigger and bigger and bigger. Oh, this one up here should be from the left. And this one should be from the right. So because the value gets larger, the closer you get. Oh, sorry about that. To 2 from the right. All right. So any questions on that one? Okay. Make sure everyone's done. Okay. Oops. Okay, so if we have our, say our vertical asymptote. Probably. The value of x, well, it could be more than one, so I'll say value, possibly values, that makes the denominator of a rational expression equals 0. All right, so let's say, for example, we wanted to find the vertical asymptotes of, let's say, problem A, f of x equals x squared plus 1 over x squared minus 1. And let's say for problem B, for f of x equals cotangent of x. Okay. So for problem A, to find the vertical asymptote, we know that the denominator can equal 0. So we know that x squared minus 1 can equal 0. Okay. So since this is the difference of squares, we can just factor that to x plus 1 times x minus 1 can equal 0. Okay. Which means that x equals negative 1 and x equals 1 are your vertical asymptotes. Okay. Now for problem B, when you start getting into trig functions, you have to be careful, because sometimes you can have an infinite number of vertical asymptotes. Okay. So for this one, you just want to remember that cotangent of x is equal to cosine of x over sine of x. Okay. Now we know sine of x is just repeating. So we know that sine of x can equal 0. Only problem with that is sine of 0 equals 0. Oh, sorry about that. Sine of pi equals 0. Sine of 2 pi equals 0. Sine of 3 pi equals 0, and it just keeps on going and going and going. Okay. So you really have an infinite number of zeros you could have. Okay. So in this case, what you do is you just say x can't equal any number times pi, where n is an integer. Because remember, it's the same in the negative direction. Okay, so we know that in pi are your vertical asymptotes. Oh, sorry about that. Actually, let me turn the monitor this way. I can kind of keep an eye on it without having to. So I'll have an idea when it's out of range. Okay, so any questions on this one? All right. Am I still writing? Okay. Now this one's a little bit different. Okay. Let's say we wanted to determine the vertical asymptotes of, let's say, f of x equals x squared plus 2x minus 8 over x squared minus 4. Okay. Now the difference with this one is you can actually factor the numerator and denominator. Last time you could only factor the the denominator. Okay, so if you have x squared plus 2x minus 8 over x squared minus 4, again this is the difference of squares. So you have x plus 2 times x minus 2, and this can be factored to x plus 4 times x minus 2. Okay, so you can actually remove the x minus 2. Okay, now in this case, x equals 2 is a removable discontinuity. Remember, when that can be factored out and removed, it's a removable discontinuity. Bless you. Not a vertical asymptote. Okay. So in this case, because you can reduce, so since x squared plus 2x minus 8 over x squared minus 4, you could actually reduce that to x plus 4 over x plus 2. We know that x plus 2 can't equal 0. Which means that x can't equal negative 2. So in this case, x equals negative 2 is your only vertical asymptote. All right. So any questions on that one?
Yeah.
Yes.
How, what you're saying, because I'm still trying to understand why that's the only vertical asymptote, because so only if both denominator and numerator simplify, then that's.
Oh yeah, so if you can somehow kind of manipulate the expression and remove one of the continuities, because normally if you just factored x squared minus 4, you get x plus 2x minus 2. Either one of those would be the vertical asymptote.
Right.
But in this case, if you have one that can cancel out, then that automatically goes from being a vertical asymptote to just a removable discontinuity.
Okay.
Yes.
I might have just missed it. Why isn't x plus 4 a vertical asymptote? Or, I guess, negative 4?
Oh, because you're looking for wherever it's undefined.
So basically, because it's only one answer,
Yep. So it's just one answer.
that's why.
Yeah. But if you're for negative 4, that would make the limit equal 0.
Okay, gotcha.
So you just wanted to make sure the denominator doesn't equal 0.
All right. Thank you.
Yes.
So because we factored x squared minus 4
Mhm.
into x plus 2 and x minus 2,
Mhm.
wouldn't x minus 2 also be a discontinuity in the graph?
Yep, but it's a removable discontinuity. Yep. So whenever you can factor it out and cancel it out, it falls under that removable discontinuity.
Okay.
Okay. So you have your removable and non-removable. So in this case, x plus 2, you couldn't, well, if you had, where is it? In the previous example, this one here, even if you factored it to x plus 1, x minus 1, it wouldn't cancel with anything up top. So that would be a non-removable discontinuity.
But if for,
Mhm.
just to play devil's advocate,
Mhm.
if in that example,
Mhm.
in the numerator, you didn't have x squared plus 1, you just had x plus 1, then
Oh, if you had x plus 1, then that x plus 1 would cancel out. So -1 would be a removable discontinuity. Yeah.
Just,
Oh, no, I just want to make sure you get it. But, yep, you were on the right track. All right, any other questions on this one? All right. Okay, so let's say, for example, if you wanted to find the limit, say for question A, you have the limit of x over 5x to the third as x approaches 0 from the right. And let's say for problem B, just the limit of x over 5x to the third as x approaches 0.
Are we approaching it from the left on the B?
On B, we're just approaching 0. So whenever you approach just 0, you have to kind of write from the left and right.
I know, but one has a plus sign and the other one, does it mean to have a negative sign?
Nope, just the 0. Yeah. And that reason's why I left that one up, just because I want to show that when it has the plus or the minus sign, you're just approaching from one side. But when you see just the 0 or the value itself,
Yeah.
you have to show both sides. Yeah. Okay, so for A, say the limit, if you wanted to, you could cancel out the x's, but you don't have to. X approaches 0 from the right. You have your x, and you have x over 5x cubed. Okay, so that gives you, let's say, if we're approaching it from the right, let's say we start with 2, then 1, then let's say 0.01, then 0.001. Oh, just could be a bit more room. I don't know why I usually have 5 spaces, but use 4 this time for some reason. Okay, so if you plugged in 2, you'd actually get 0.05. If you plugged in 1, you'd get 0.2. Okay. But if you plugged in 0.01, you'd see it shoot up to 2,000. If you plugged in 0.001, you'll see it shoot up to 200,000. Then as you get closer and closer and closer, it gets bigger and bigger and bigger. Okay, so the limit of x over 5x to the third as x approaches 0 from the right is going to equal infinity. Yes.
So you wouldn't really have to simplify it as,
Be 1 over 5x squared?
yeah.
You could, but it'll do the same thing.
So how do you know what value to plug it? Oh, as x goes to 0.
Yeah, just as it's getting closer from the right.
So whenever the limit is infinity, that just means that there's no limit, right?
Yep, that means there's no limit.
So I'm just looking for that increase, the closer I get to 0 from the right, that's what the telltale.
Yep, so